Breathing is one of the most important things that you do, and every day you take thousands of breaths. But what exactly are you breathing? About a year ago, we did a big survey where we asked hundreds of people what they were breathing. A lot of people knew that oxygen was one of the gases they were breathing. But when we asked them what else they were breathing besides oxygen, most people didn't know.
Hydrogen, oxygen, a large amount of carbon dioxide.
Some carbon dioxide, some nitrogen.
Fumes, smog.
I'm not sure, actually.
I'm Science Mom.
And I'm Math Dad. Today we're going to find out what you're breathing and why.
Hello, and welcome to a science lesson all about the gases of our atmosphere. Special welcome and shout out to those who are joining us live, and a welcome to you if you are watching the replay. Today, we are going to dive into the 6 most important gases of our atmosphere, starting with the most common one that you are breathing right now.
Ooh.
Any guesses what it is, Math Dad?
I actually think I know this one because we covered this one in our chemistry course. It's nitrogen. Nitrogen is the most common gas.
Nitrogen is the most common gas in our atmosphere. It makes up 78% of the air we breathe. And I have a special little cartoon I drew of nitrogen just for you, Math Dad.
Oh, that's so cute.
So,
and the triple bond.
Yes. Yeah. Nitrogen is N2. That means that there are 2 atoms of nitrogen and they're bonded with a very strong triple bond.
He's looking at me. He likes me. Look at that.
And nitrogen is not at all reactive. It's not going to burst into flames. You can't catch it on fire, which is a good thing for us, right? Because if most of our atmosphere were flammable, that would be bad.
You'd like light a match and the whole
room would explode. The reactive member of our atmosphere is oxygen. And here is oxygen, O2. 2 oxygen atoms, and they have a double bond. Oxygen is reactive.
Yes, indeed. It's looking at you, so it likes you.
It is, and it's green because oxygen comes from trees. Photosynthesis from algae and trees is the main source of oxygen.
Wait, are oxygen molecules really green?
No.
Okay.
In real life, the atoms are so small, they actually don't have color because they're smaller than a wavelength of light.
That's right.
But just for fun, I like to draw them in a cartoonish way because I think it helps make them easier to remember.
Gotcha.
Okay, what gas is this, Math Dad?
It's a lonely little molecule or little atom there that's by itself. So this is one of the gases of the atmosphere?
This is one of the gases in the atmosphere. And it is
it
all
argon?
alone
it's
because
argon.
All of its friends are gone. Yes. This is argon. Argon makes up 1%, just about 1% of our atmosphere. And so let's do the math real quick, Math Dad. If we have 78% of our atmosphere is nitrogen, 21% is oxygen, and 1% is argon, what does that add up to?
That's 100%. Like there's pretty much nothing left then. Like
now,
are we within rounding distance of 100% then?
I rounded those percentages, and yes, 99.99% of our atmosphere is just those 3 gases: nitrogen, oxygen, and argon.
That's kind of crazy.
Those are the main gases. But, and here's the crazy thing, if our atmosphere was only those 3 gases and no other gas, we would live on a freezing cold planet and there would be no life.
Wait, what?
Because there are other gases that are incredibly important for life, and carbon dioxide is one of them.
Oh.
So here is carbon dioxide. And remember, Math Dad, what were the green atoms?
Those were oxygens.
Yes, and the red is a carbon, so we have CO2.
Oh.
A lot of times people will talk about carbon dioxide, and they might call it carbon dioxide, or they might call it CO2. Those 2 words mean the same thing. This gas is actually incredibly important because it is food for plants. This forest behind us, these plants on the planet need carbon dioxide, and without carbon dioxide, they would starve. But too much carbon dioxide is not good because carbon dioxide is a greenhouse gas.
So what does that mean?
That means that heat that is bouncing off from our planet's surface, it gets trapped by greenhouse gases and reflected back. It warms the planet. Kind of in the same way that if you go into a greenhouse, the glass traps heat and you'll be warmer inside the greenhouse than you would be outside.
Oh, so it's not the greenhouses have a lot of this gas in them. It's the gas itself makes Earth act like a greenhouse.
Yes, the gas acts like a greenhouse, trapping heat inside.
Gotcha.
But carbon dioxide is not the only greenhouse gas. There are others.
Okay.
Do you have a guess about what the others might be?
Oh man. Probably other carbon emissions, right? Things like methane.
Like methane. This is another greenhouse gas, and this one does have carbon inside it too. This is C for carbon, and then these little purple balls represent hydrogen. So CH4 is methane. Methane is a carbon containing gas that is also a greenhouse gas. But we have another one that's very important, and this one has no carbon at all.
Oh?
What's this one?
Happy little oxygen attached to 2 hydrogens. So that's H2O. It's water.
That's right. That is water. Water is also a greenhouse gas. And you may have noticed, if you've ever spent time in the desert, that it's a lot colder at night in the desert than it is in a humid climate at night. If you're in a very humid climate, at nighttime, the temperature drops a little bit, but not a super duper amount. But in the desert, there's a big difference in the temperature between day and night. And that's partly because there's less water in the air. And so you don't get as much of a blanket of...
Really?
Yeah.
Huh. I guess I had noticed that when it's cloudy at night,
when it's cloudy at night, yeah, when it's cloudy at night, it will stay warmer than if it's a clear night. The clear nights tend to be colder.
Huh.
So greenhouse gases, water, CO2, and methane. And then the regular gases that are not greenhouse gases that make up most of our air, oxygen, nitrogen, and...
argon.
Argon, who is all by itself because all of its friends are gone. Really, it's a noble gas, and so it doesn't bond with other gases. Now,
Gotcha.
Before we look at our notes, I have a quick experiment I want to do because there's something important you should know about these gases, and that's which ones are combustible. Which ones can we light on fire?
Oh.
So we're going to do a quick experiment with candles. And anytime we're doing experiments, it is a good idea for us to use some safety gear. So we will put on our safety goggles and change our camera view to a spot over here where we have 3 jars.
All right.
Now, one of these jars is a control, and it just has water in it. That's our center jar right here. It just has water. This jar has hydrogen peroxide, and we're going to make oxygen gas in this jar.
Okay.
This jar has vinegar, and we are going to add baking soda and make carbon dioxide. And I want you guys to, if you're watching the replay, pause the video right now and make a prediction which candle is going to burn the brightest, which candle is going to go out, what's going to happen when this fills up with oxygen, this stays the same gas, and this fills up with carbon dioxide. So make your prediction, and then we're going to find out. So first, I've got to light our candles.
Oh, you can do it, Science Mom.
Can I do it with one match? That's the real question.
Can you do it without burning yourself? Ah,
She
did it.
I did.
All right, and which ones?
Oh, that one with water. I spilled a drop of water on the candle when I was pouring the water in, and so it got wet and went out. So we have to relight that candle real quick.
That's not a very good control. It just goes out.
No, it's not.
You've rigged it. Uh-oh.
I did not rig it, but unfortunately, we might, you know what we need to do? I'm going to get this candle lit and light it that way. If your wick of your candle gets wet, that definitely makes it more difficult for your candle to light. And this candle has a little spot of water right there at the base. So you know what we're going to do? We're just going to trade out the candles.
All right.
Because, yeah, a wet wick is not going to burn.
Not very well, no.
Nope. Good thing we had an extra candle here.
Ah, careful, Science Mom. Uh-oh.
Candles in jars are trickier than one might have thought.
Whew.
But we are good. We
All
are
right.
good. Okay, now for the fun part. We are going to add our ingredients to make these reactions happen. So I have a little container here with some yeast in it. The yeast is going to go into our hydrogen peroxide, and it's going to make oxygen gas. And then I have a container here that has baking soda mixed with water, and that's going to go into our vinegar and make that reaction happen. So Math Dad, you ready? On the count of 3, don't pour it on top of the candle flame. Pour it on the side.
You didn't count to 3.
Oh, I didn't. Whoops.
All right.
Well,
I'm seeing lots of gas coming up here. And wait a minute. Did you put out your candle? What happened? Mine's gone too.
The carbon dioxide one went out, and Math Dad, we have a whole bunch of liquid.
Did I splash?
I think we did. I think we
Oh,
splashed
no.
because we have a whole bunch of yeasty liquid on top of our candle. Well, that is too bad, you guys. And this just goes to show sometimes when you do an experiment, it works, and sometimes you make a mistake, and that is okay. Mistakes are a part of life. They definitely happen. And because we got our wick wet when we dumped in our yeast solution, and see, it's so wet that it's even now, it's having a really hard time lighting, and it won't light because...
Can you put it in that? Light it off that candle?
Maybe I can. All right, very carefully, I'm reaching into the side of this candle.
Well, I meant to dip this one in that jar, but okay.
And we will see if we can get our flame to light. Do you hear all that popping?
I do hear that
It
crackling.
really got wet. And then I should have, you know what I should have done? I should have brought tongs. Tongs would be much better for this.
Agreed.
But since I don't have tongs, we will just stick it there and then see if we can stand it up with a spoon. And there we go.
Nicely done.
So now you can see that our flame that is inside the jar with oxygen is burning brighter than our control flame, kind of, because our control flame got stuck to a spoon and is now struggling.
All right.
All right, it is time to burn out our candles, blow out our candles, and go back to our main screen. So sometimes when you do experiments, they work out just as planned, and sometimes you run into hiccups like we did just here. What should have happened is that the candle in the jar with carbon dioxide goes out right away because carbon dioxide is not a flammable gas. And if the carbon dioxide is filling up that container, it's displacing the oxygen. If there's no oxygen, the candle goes out. The jar that had the candle with the oxygen, on the other hand, yesterday when we did this, burned twice as tall as our control flame.
It did.
But for it to burn twice as tall, it has to be dry. It cannot be wet.
Yep.
But that's okay.
We failed.
It happens.
It's not the first time we've failed, but that's okay. It's actually a really cool idea. The idea for the experiment should actually demonstrate whether the gas is supplying fuel to the fire, right?
Yeah. And we have a follow-up experiment we'll do in just a minute. But first, let's talk about our other gases and whether or not they are flammable.
Okay.
So how about argon being a noble gas? Do you think argon is a flammable gas?
Ooh, okay. So noble gases are famous for not being reactive, right? So I'm going to say no.
That's correct. It is not a reactive gas. And nitrogen, also not reactive at all. If we had a big container of nitrogen and just poured nitrogen gas onto a flame, the flame would go out. What about methane?
Well, methane, hydrocarbons are famous for burning, right? So this one...
Yes. Methane
yes, it is flammable.
Is flammable.
Okay.
In fact, natural gas is mostly methane. So if you have a stove that burns natural gas or a car that runs on natural gas, most of what you're burning is methane.
We have methane in our house right now?
Some. Our stove actually runs more on propane.
Oh, okay.
Yeah. So those are that's how you, and then water is our last gas that we haven't talked about yet. Water, of course, is not flammable. But we have two of our greenhouse gases two gases that are. One a greenhouse gas, methane, and then the other one, oxygen. Not a greenhouse gas, but very important for us for breathing. And the reason we're able to breathe and use oxygen is because it is reactive.
Cool.
All right, Math Dad, are we ready for our second experiment? And
I'm
then
ready.
We'll check out the notes real quick.
All right.
Everyone cross your fingers for us that this works better than our first one.
All right.
Because sometimes when you're doing live experiments, sometimes they work really well and sometimes they don't. So with this one, we have the same reaction that we did before. We are going to do hydrogen peroxide and yeast, but we are going to put a special lid on the top, and we're going to see if we can get enough oxygen to actually have a little pasta rocket.
Pasta, like spaghetti, like stuff we eat? Pasta?
Yes, like the stuff we eat. So Math Dad, do you think that pasta is flammable?
No, because when you stick it in the oven to make a casserole, it does not burn. So pasta is not
It's true.
flammable.
If I were to take a match and try and light this noodle on fire right now, it would not burn. but it's fuel and I eat it and I get energy from it. It is flammable. It just needs to be hotter or have more oxygen. And the have more oxygen part we can do right now. So I'm going to take a spoonful of yeast and put it into this container. Uh-oh, but one thing I need, Math Dad, is my lid.
Uh-oh. We've lost the lid.
Oh, no.
Kitchen.
Check the bathroom real fast. Oh, my goodness, you guys. Sometimes you plan things out really well and it all goes perfectly. And other times you have days like today that are just a hiccup of a day where things go missing. And when I rinsed out my experiment after testing it this morning, I left my lid in the bathroom.
But so that lid has a hole there.
It has a hole in it. And we're going to swirl around to get this reaction started. And then we're going to stick our noodle on top.
Okay.
And I put my safety goggles back on because it is always a good idea to have eye protection on when you're doing science experiments.
All right. I'm seeing some bubbles here. It's starting to rise up a little bit.
We're definitely getting gas produced. And the gas we're producing is oxygen.
Okay.
And if we have enough oxygen coming out, we should be able to get a pasta rocket.
So the oxygen's filling this up, and then there's a hole in the center of that lid?
Yes, and I want to point out, this is super important for anybody who wants to recreate this demonstration. I did not put the ring on this jar, and that is on purpose. You do not want to secure the lid to the container. You want the lid just sitting there free so that it can just pop off if too much pressure builds up.
Okay.
And now the moment of truth. We'll find out if we have enough gas to light our pasta rocket.
You can do it. You can do it, Science Mom.
I don't know if we quite have enough yet. I'm starting to wonder if I put in enough hydrogen peroxide, but we'll find out. Maybe we just need to be patient. Sometimes it just requires a little more patience. I think we are having not quite enough gas come.
All right. And obviously there's enough gas to fill those bubbles, but that doesn't mean it's even the bubbles have to pop.
Well, I used an older container of hydrogen peroxide, and I think it's possible that container wasn't quite as active.
So over time, the hydrogen peroxide loses its...
Over time, hydrogen peroxide changes into water. So we'll see if we have enough now. Oh, now we do. See how differently the flame looks?
Yeah. Okay. So that's oxygen that's coming up that's making that flame dance like that.
And it's making it so bright, yes. We have a pasta rocket, and we will see if it will actually burn like it did yesterday when we did our little test demos. Cross your fingers, Math Dad. Is it going to work?
I don't know. It looks like it's going out to me.
I can definitely still see red around there. It's still burning. Just
that's not much of a rocket, though.
Oh, there it goes. There it goes. It's taking off.
Whoa.
We have a rocket. A very stinky rocket. And the reason that it is burning so well is because of the extra oxygen. We sometimes think...
Oh, the lid's being pushed up.
Oops.
Okay.
And the rocket is done. I'm going to stick it in our little container of water over here.
The bubbles push the lid up.
Yes. We sometimes think... Let's go back to our main view, and we'll just let this fountain off to the side. Right. We sometimes think, oxygen is good. More oxygen would be even better, but that is not the case. You do not want too much oxygen in the atmosphere because too much oxygen would be quite dangerous. And we'll share a video real fast of how we did yesterday with our pasta rocket, because yesterday we did a little test version and it worked quite a bit better. So here is our rocket just starting to burn. And then as it gets going, you'll notice that we have a really impressive amount of flame and heat coming from it.
Whoa.
There it is, really going and almost getting pushed off, but not quite.
Yeah, that's an impressive amount of flame.
Yes. And if we had an atmosphere that was, 70% or 80% oxygen instead of 80% nitrogen, it turns out that simple things like lighting a birthday cake would be really dangerous because you wouldn't just get the candle blowing. It's possible that all sorts of other stuff would start to ignite as well, and things would burn a lot faster and our bodies would actually suffer as well. Your lungs, your skin, and all of your tissues would be attacked by that extra oxygen, and they would wear out and have problems a lot sooner than they do now. Aging is really like the effects of aging, like wrinkles and things, that's essentially caused by oxygen.
Oh, wow.
Because oxygen is reactive.
I did not know that.
Yes.
So
and
historically, the Earth had more oxygen at times?
It did, and we'll talk about this more in future classes. But yes, there used to be 35% oxygen in the atmosphere, which was great for insects. Insects could get really large, but you and me, we would not be so comfortable if we were breathing 35% oxygen. That feels kind of, ugh.
And fires would have been bigger then?
It would have been easier for things to catch on fire. That is true.
Wow.
Yes.
Super
and
interesting.
I did see a couple questions about, why is this called a pasta rocket? I think it's kind of a fun name. I mean, this isn't a rocket as in like it's traveling anywhere, but just like a rocket uses fuel, the pasta kind of becomes the fuel, and it looks like a rocket because the tail is going, the tail of flame goes up in a point. So that's how it got that name. All right, let's take a look at our notes real fast.
All right, so we are on page 8 of the notes.
And hopefully you've been able to fill in some of this already just from listening. But real quick, I just want to point out and review what we covered. So what gas makes up most of the atmosphere? That is nitrogen, or N2. And then the gas that is responsible for us being able to breathe is oxygen, O2. And together, nitrogen and oxygen make up more than 90% of our atmosphere. Those are the main players. But we can't forget about argon. Nice little noble gas argon, abbreviation AR, that's the symbol for that element, is all by itself and not very reactive, but it makes up a whole percentage of our atmosphere. That's pretty significant.
Light bulbs often have argon in them, right?
Sometimes they do.
Is that because it's so stable?
Yeah, because it's very stable and not reactive. And then we have our 3 important greenhouse gases. Water vapor is a very important greenhouse gas. And of course, water vapor in our atmosphere can condense into a liquid, and then it's no longer a gas in our atmosphere. It's changing all the time. The amount of water is always changing. And methane is a very powerful greenhouse gas. Small amounts of methane can have a really big effect. And then last and most famous of all, CO2, carbon dioxide. And which one of these are flammable, Math Dad?
Ooh, okay. So we talked about this. I know methane was flammable.
Yep, methane is flammable.
And oxygen.
And oxygen is flammable. Right. So these two in the middle. Are any of the others flammable?
No.
Nope. Nope. And next, if we can go back to our regular view, now it is time for I almost said chemistry. It's not a chemistry. It is a where in the world mystery.
Oh.
We have a where in the world mystery real quick, and then we are going to pull up our polls. So if you don't already have item pool open, make sure to open up item pool because we have some poll questions for you in just a few minutes. But first, I'm going to see if Math Dad knows the answer to this mystery.
I'm going to count on the chat to help me out here.
This prehistoric ring of stones, each weighing more than 20 tons, was once the work of druids and a burial ground. I'm going easy on you for the first one, Math Dad.
Oh, yeah. I think I know this one. The druid thing gave it away to me, but I'm curious if the chat knows this.
And didn't you come up with a nice little jingle for where in the world?
I came up with like 7 of them.
You did.
Where in the world? Boom. I don't know. We'll have to work on that.
Stonehenge. I'm seeing it all over the chat. You guys have got this one in the bag. Stonehenge is correct.
Each of those stones weighs 20 tons.
The stones are enormous. And to get a sense of the scale, I uploaded a simple video.
Okay, so.
And you can see people there in the distance. Hopefully we're not muted.
Those are tall.
So you could see those people in the distance. Those people were so small compared to the stones. And granted, the people that you saw were behind the stones, but still, if you're standing next to those, you are dwarfed by the stones. They're enormous. And they were moved there without the aid of modern machines and technology. So it's really an amazing structure. And the whole entire structure itself, a lot of it is collapsed. But back in the day, this is sort of a representation of what it would have looked like. You would have had a complete ring all the way around. And then the center stones line up with the equinoxes of the sun. So on the longest day of the year, the shortest day of the year, the sun sets exactly in between the stones, which is pretty cool.
Yeah.
And then last but not least, here is a picture from the notes. So if you are participating in the Where in the World clues in the notes, that's your match for Stonehenge.
Super impressive.
Yes, it's an incredible, incredible structure.
I can't imagine trying to move those stones without, like, today we have cranes and heavy equipment that can do it.
It is still a little bit of a mystery. We've got some theories for how they moved the stones, but it's really impressive that that structure was built. A really cool thing.
So kudos to you if you got it right. Those of you who were answering it in the chat.
That is right. And now we are ready for our quiz questions. So open up item pool. We have 5 questions for you. Most of which I've covered in class, but we do have one just take a guess question that's a little more challenging. So I'm excited for these.
All right. So we are at itempool.com/sciencemom/live. If you'll go there, you can participate. And of course, you are welcome to just watch and not actually.
But you should try and say the answer out loud if you're not able to.
That's the most
vote.
important thing, is that you're trying to answer these in your heads. All right. So for our first question, which gas makes up most of the atmosphere?
And while we're having answers come in on this one, I will comment really quickly. Some great questions about Stonehenge in the chat, but I am not an archaeologist and didn't have time to research extensively. So I would say just use it as an opportunity to research and see what you can learn about Stonehenge.
Then that'll be true for all of our Where in the World clues. You could spend quite a while just researching and finding out the background, because there's some pretty cool places in the world.
Yeah.
All right, Science Mom, I don't think I stumped them on this one, which is okay, because it was the warm-up problem. I wasn't even trying to stump you guys.
The gas that makes up most of the atmosphere is nitrogen. Go ahead and finish and reveal. And the other 2 gases that are the majority of our atmosphere are oxygen and argon. Weezard asked a great question. Are there any other noble gases in the atmosphere? And there are, but their amounts are so small. They're just in trace amounts. So there is some helium in the atmosphere, but it's so small. It's really not detectable. The noble gas that you've probably heard of that sometimes makes it into our atmosphere is radon. Radon is a noble gas that we really don't want to have around because it is a little bit radioactive. All right, next one.
I was thinking of neon, like neon lights.
Oh, neon is good one too, but again, very, very small amounts.
All right. Which of the following are greenhouse gases? We got CO2, oxygen, H2O, argon, methane. Ooh. Which are greenhouse gases? So we talked about 6 gases today. Some of them were greenhouse gases. Some of them were not. Actually, let's think for a minute. So greenhouse gas, if I recall, I'll try to explain this, was some gas that would trap heat in, it would reflect it back, much like a greenhouse lets the light in and then traps the heat from it.
Exactly. So just like it's warmer in a greenhouse than it is outside a greenhouse gas, when light enters Earth and heat from the sun enters Earth, it hits the surface of the Earth and some of it bounces back, and then the greenhouse gases reflect it back down. That's kind of a simple explanation for how they work.
Yeah. Well, the chat was noting that I did answer question wrong last time, but on the spam question, I had the exact wrong answer selected instead of.
It's poor math, Dad. Sometimes this happens. All right, go ahead and finish and reveal.
All right, and the greenhouse gases, A, E, and C.
Yes, carbon dioxide, water, and methane. Good job, you guys. That's exactly correct.
I think water would be the easiest one to miss because
we don't
think of water as a gas.
Yes, but when you think about it, the humidity, wherever you live, there's going to be a certain amount of humidity. For us in Nevada, the humidity is really low. If you live in Florida, the humidity is going to be a lot higher. And that is essentially a measure of how much water gas or water vapor is in the air.
Okay, so
next question.
Kudos to you if you got that one right, because that was definitely a step harder than the previous one. All right, up next. If there were a machine that could remove all the CO2, so carbon dioxide, from the Earth's atmosphere for 1 year, should you turn it on?
So this is kind of a fun hypothetical question, and we will talk a lot more about carbon dioxide in future classes, but you've probably heard on the news carbon dioxide is a greenhouse gas, and we have a little too much of it in our air right now. So if you had this magic machine, this machine that could just take all of the carbon dioxide from the atmosphere for an entire year, there would be no CO2. Should you turn it on? Yes or no?
So it's a good question. So first of all, does such a machine exist?
No.
Okay.
And I cannot think of any plausible way that you could create such a machine. But, assuming you could, should you turn it on? We have a very strong preference for one answer over the other. And I'm so glad that you guys said no, because no is correct. If you did take all of the carbon dioxide out of the atmosphere for an entire year, all of the plants would die.
And they need carbon dioxide for photosynthesis?
Yes, and that would be catastrophic. We can have half as much CO2 in our atmosphere, and that would actually be beneficial. That would solve the global warming problem. That would put levels back down to where they had been stable at for hundreds of thousands of years, and the plants would be just fine. But if you took all of it out, every single tree would die. And that would be terrible. So
now what would it do to the temperature?
The temperature would drop as well. But we really wouldn't care about the temperature dropping if all the plants were dead.
Oh, because we'd be starving?
Yes.
Okay.
So yep, kudos to Quinn and everyone else in the chat who was saying, no, don't do it. You guys were correct.
All right.
Which of these gases are combustible? That means either they could explode or catch fire. And I guess maybe it would have had been better if I just said which are reactive, which gases will burn.
All right. So we got nitrogen, carbon dioxide, oxygen, methane. So which ones are combustible?
This is a good question.
Okay, they're all getting some votes, but it looks like two categories are maybe getting more votes than the others.
And I saw a couple good questions in the chat. If you can't participate in the item pool, can you put the answers in the chat? You certainly can. You can also just say them out loud. If you just say it out loud, you will definitely learn more than if you're just watching. So just say the answer out loud. Tell us which ones you pick, and then we will finish and reveal.
And oxygen and methane is what the chat says.
And they are 100% correct. Those two are reactive. The other gases are not.
Well played, guys. They've been paying attention.
All right, last question. And this is our take your best guess question. And I really like this question a lot. So just take your best guess. What weighs more, all of the air on Earth or all the water in Lake Superior?
So Lake Superior is huge. If
Enormous.
You don't know, the biggest of the Great Lakes. But okay, so which weighs more? The air on Earth by just a little, the air on Earth by a lot, the water in Lake Superior by a little bit, or the water in Lake Superior by a lot?
And I'm going to give you one small little hint. I'm going to tell you. I'm just going to tell them how much the water in Lake Superior weighs.
Okay.
You ready for this? The water in Lake Superior weighs 4.6 billion tons.
Wait, okay.
No, that's 1 cubic mile. 1 cubic mile of water weighs 4.6 billion tons. The water in Lake Superior is 1.3 times 10 to the 13th power tons.
Whoa.
So that's a huge, it's so big, you guys, we can't even really say it. So there are two.
A 14-digit number.
There are more than 2,000 miles of water in cubic miles of water in Lake Superior. And each of those cubic miles weighs more than 4.6 billion tons. Apologies for using the English system of measurement, which is not superior to the metric, but that's what I had in my notes. Let's go ahead and finish and reveal.
All right, revealing the answer. Chat says that the air on Earth
by a lot, and the air on Earth by a lot is 100% correct. Good job, you guys. Knocked this one out of the park.
So I noticed that the second most popular answer was that the water in Lake Superior by a lot. That would have been the other end of the spectrum.
Oh, you're right.
Yeah.
So we were pretty evenly split. All right, let's go back to our main view and we'll talk about this just a little bit more because this is actually pretty cool. So the water in Lake Superior is super, super heavy, and water is way heavier than air. If you have a jar of water and a jar of air, like especially a big one, like a big 5-gallon container.
Oh yeah, 5-gallon buckets, about all your arm can lift.
Yeah, but if they're full of air, you can carry those no problem. Full of water, really heavy. So Lake Superior is enormous, more than 2,000 square miles. Each of those square miles of water weighs more than 4 billion tons.
So cubic miles.
Cubic miles, thank you. But the air on Earth is estimated to weigh 5 quadrillion tons. That means it is 400 times heavier than the water in Lake Superior.
That's crazy. I mean, we live in air. How come I can't feel all that air on me if it's so heavy?
Because we live in air just like fish live in water. only we're too heavy to swim. We're just walking around on the bottom the whole time.
So like if fish were too heavy to float, they would have to hang out on the bottom of the ocean. Like that's
exactly
how it is. Wow.
And where you live and where your body is adapted to live, that's where you feel comfortable. A fish is very comfortable living in water. And if you take a fish out of water, the fish feels terrible. We are very comfortable living in air. And if you take us out of our ocean of air, if you take us into outer space, we die immediately because we don't have that blanket of air. We need air. We live inside it.
Yeah.
Now, I want to answer just a couple questions that came into the chat. So,
Alicia, is nitrogen reactive by itself? Is the question.
Great question. The answer is no. Nitrogen N2 is very, very stable. And if you just have nitrogen by itself, it is not at all reactive. Good question. And then Xander asks, is ozone listed as one of the gases in the atmosphere? And what is ozone? Ooh. We have an entire lesson on ozone that will come in a couple weeks where we'll talk more about it.
So it is one of the gases of the atmosphere?
In very small amounts. And if it's on the surface of our planet, it's actually considered a pollutant, and it's not good for us to breathe in, and we want to have those levels small. But up in the stratosphere, which we'll learn about on Friday, ozone is very important. We'll talk about that more later. And last question I saw, will Science Puppy continue to make an appearance on Friday? Science Puppy will. We will see Science Puppy on our game show review days for sure. All right, guys.
Awesome.
That concludes our lesson for today. I hope that you enjoyed learning about what air is made of and what we're breathing. And then on Friday, we'll dive into the layers of our atmosphere and what happens when you go up higher towards space. But Matt, I just put this in my hand because I almost forgot. We have some birthday shout outs. So a very happy birthday to Lena, who turns 10 tomorrow, to Kyler from Alaska, who turned 10 yesterday. Happy birthday, you guys.
Double digits, double the trouble.
Very, very exciting. So, and thank you, Lily Games and Finn and Amy and Margaret and Elizabeth for joining us. We had a great time exploring the gases of our atmosphere today with you, and we hope to see you again on Friday. Work hard, grow smart. We'll see you soon.
Bye.